This is the 12th video in a series devoted to introductory proof writing. And today we're going to talk about proofs involving sets. So how do you show that something is an element of a set? How do you show that one set is a subset of another set? And how do you show two sets are equal? Those will be the main things that we cover. So let's start with how to show that something is an element of a set. So let's say we've got a set written in set builder notation as follows. We'll call our set A, and it's built up of elements X satisfying some condition P, so P of X. So there's really not much to showing that A is an element of A. All you need to do is show that P evaluated at A is true. So recall P, when it's not being evaluated at anything, is an open sentence, but when you evaluate it at something, it becomes a mathematical statement which may be true and may be false. If it's true, then your element is in the set, and if it's false, then your element is not in the set. Okay, well, there's another way of writing down sets, which is also set builder notation, but adds a little bit of a different condition, and that's set builder notation of the following form. We have the set A is all X in S such that P of X. So P of X is still that mathematical statement, or that open sentence being evaluated at X. But we have this extra condition that X must come from some sort of universal set. And so the proof here really is essentially the same thing, except you also have to check that you're within that universal set first. So if you want to prove the claim that A is in A, then you would first show that A is an element from S, and then you would show that P of A is a true mathematical statement. Okay, so let's do a couple of examples before we move on to the meat of the video, which is showing one set as a subset of the other and then showing set equality. So let's consider the set, which I'll call A again, and it'll be all ordered pairs of integers such that their product is congruent to 0 mod 6. So let's look at some examples of things in A and things not in A. So let's notice that 2, 3 is in A, and that's because 2, 3 is in Z cross Z, and 2 times 3 is equal to 6, but 6 is congruent to 0 mod 6. Okay, so that's really all there is to it. Now let's look at another one. So the ordered pair 4, 9 is in A, and that's because 4, 9 is an element of Z cross Z, and 4 times 9 is equal to 36, but 36 is a multiple of 6, so it is congruent to 0 mod 6 as well. So in fact, we could find an infinite family of elements in this set. Let's note for all n in Z, the ordered pair n, 6 is in A. And that's because it starts off being inside of Z cross Z. So that's the first rule that it has to satisfy, and then the stricter rule that it has to satisfy is that 6 times n is congruent to 0 mod 6. So now let's look at a non-example. So let's notice that the ordered pair 2, 5 is not inside of A, and that's because 2, 5 is in Z cross Z, but 2 times 5 is equal to 10, which is not congruent to 0 mod 6. In fact, it's congruent to 4 mod 6. We could do another example. Notice 1/2 12 is not inside of A, and that's because 1/2 12 is not inside of Z cross Z. So it's not even within the universal set. But that being said, it does satisfy the condition, which is kind of interesting. I'll put that in quotes. We wouldn't actually check that because we don't get past the first door in this case. Notice that 1/2 times 12 is equal to 6, which is congruent to 0 mod 6. So it satisfies the stricter condition, but not the opening condition. Okay, so now let's talk about subsets. Now we're going to talk about proving how one subset is a subset of another. But let's note that that's really a conditional statement. Showing that A is a subset of B is equivalent to the conditional A is an element of A, so lowercase a is an element of A, implies lowercase a is an element of B. So we'll keep that in mind when we form our outline for our proof. And we'll have a direct and a contrapositive outline. Although I guess you could have a proof by contradiction outline if you wanted to as well, but I'll let you fill in those details. So if we want to prove that capital A is a subset of capital B, then the direct method would be to suppose we've got an element, lowercase a, of A, and then do some calculations with what it means to be inside of the set A. That's what this box is. And then you would end at the end with lowercase a is an element of B. And then likewise, if you want to do a contrapositive proof, you would start with lowercase a is not an element of B. That's like the not Q condition here. You would do some calculations and you would end with lowercase a is not a subset of capital A. Okay, good. So let's look at this first example, which I think we might do both ways. So we'll show that the set of all integers that are congruent to 1 mod 4 is a subset of the set of all integers which is congruent to 1 mod 2. Okay, so let's get to it. Now let's start by supposing that we've got an integer, I'll call it m, from this left-hand side. So in other words, it's of the form 1 mod 4. So being inside that set means that you're 1 mod 4. So thus we can say m is congruent to 1 mod 4 and then m equals 4k plus 1 for some integer k. Now we did this step from here to here in more than one step previously. We moved through divisibility, so we would say in the middle that 4 divides m minus 1, but I think this is okay just to jump all the way there from now on. Okay, so now looking ahead, we'd like m to be of the form 1 mod 2, but that means that m minus 1 is divisible by 2, but we can show that pretty easily. So now let's note that m is of the form 2 times 2k plus 1. But that means that 2 divides m minus 1. Pretty clearly, we can move that 1 over, and then we have m is an even number. Okay, so thus m is congruent to 1 mod 2. But that's exactly what we need for m to be in the set on the right. So maybe we would finish it off with, and m is an element of the set of all integers that are congruent to 1 mod 2. Okay, so that would be this proof. Okay, so now as promised, let's also do the contrapositive. Now we will reprove this result using the contrapositive. So let's suppose we've got an integer which is not in the right-hand side. So in other words, m is an integer with m is not in this set of all integers such that it is congruent to 1 mod 2. Great. But what does that mean? That tells us that m itself is not congruent to 1 mod 2. That's what it takes to not be in that set. But if m is not congruent to 1 mod 2, it must be congruent to 0 mod 2. Because, well, there are only 2 possibilities when you're working mod 2. Only 2 remainders when dividing by 2, 0 and 1. So let's write that here. We have m is congruent to 0 mod 2. Okay, but if m is congruent to 0 mod 2, that means m is even. So let's write m as an even number. So we'll write m as 2 times k for some integer k as needed. And now let's break this down into 2 cases depending on the parity of k. So here's our case number 1, which is k is even, thus we can write k as 2 times, maybe I'll call it a, where a is some integer. So in this case, we have m is equal to 4 times a, which is congruent to 0 mod 4. But that means that m is not congruent to 1 mod 4. Great. And now let's look at case 2, which is the case where k is odd. But if k is odd, we can write k as 2 times b plus 1 for some integer b. But now plugging this version of k here, we see that m is equal to 2 times the quantity 2b plus 1, which is the form 4b plus 2, which is congruent to 2 mod 4. But being congruent to 2 mod 4 means that you cannot be congruent to 1 mod 4. So that tells us that m is not congruent to 1 modulo 4. So either way you have it, through either of these cases, we have m is not an element of this left-hand set. So let's write out that left-hand set. It's all integers n, such that n is congruent to 1 modulo 4. So the direct way is definitely easier in this case, but I think it's nice practice to see both. So let's do another couple of these. So for our next one, we'll show that the intersection of the set of all integers that are divisible by 2 and the set of all integers that are divisible by 15 is a subset of the set of all integers divisible by 10. So let's get going. We'll do this with the direct method. So let's suppose that we have an element m from this left-hand side. So it's in the intersection of these two sets. The first of which is the set of all integers divisible by 2, and the second of which is the set of all integers divisible by 15. But what does that mean? Well, that means that m is in this set and m is in this other set. But we can quickly bring that down to m being even and m being a multiple of 15. So let's maybe take it all the way to that point. So m equals 2 times a and m equals 15 times b for some a and b which are integers. So this 2 times a is being in the first set, this 15 times b is being in the second set. So now let's note that since 2 times a equals 15 times b, so that's just setting both versions of m to each other, we know b is even. So I think that's pretty clear. The left-hand side is even. That means the right-hand side has to be even. 15 is non-even, which means all of the evenness on the right-hand side must be created by this number b. So now let's write b as 2 times c for some integer c. So now that we have this, let's plug this expression for b into this expression for m up here. So I'll maybe write it like this. Observe that m is now equal to 15 times 2c, which is the same thing as 30 times c, which is the same thing as 10 times 3c. But 10 times 3c is an element of this right-hand set. So we could say that this is in the set of all integers n, such that 10 divides n. Great, but that's what we needed to do to show this subset relationship. We started with an element of the left-hand side, and we showed that that element was also an element of the right-hand side. So that concludes this subset proof. So now let's do a couple more that are kind of a little bit more abstract. So for our next result, we'll show for all sets A and B, the union of the power set of A with the power set of B is a subset of the power set of the union of A and B. Let's recall, in order to be inside the power set of a set, you are a subset of that set. Okay, so let's get going. So let's take an element capital X from the power set of A union the power set of B. So that means that X is in the power set of A or X is in the power set of B. But now let's notice that A and B are playing symmetric roles in this entire setup. So that means we might as well just choose X to be an element of the power set of A, Given that, the same calculation would happen if we chose it to be in the power set of B. So that allows us to use our phrase without loss of generality. So let's do that. So without loss of generality, let's assume that X is an element of the power set of A. Okay, now let's get down to what it means to be an element of the power set of A. Thus, X is a subset of A, but notice that A is a subset of A union B. So this is a subset itself of A union B. But being a subset is a transitive property, so that means X itself is a subset of A union B. So I'll just add that on, and that X itself is a subset of A union B. But now we'll go back to power set world. So if X is a subset of A union B, it's an element of the power set of A union B. So we'll write that as finally, X is an element of the power set of A union B. So let's just check that we've done everything we needed to. We started with an element of the left-hand side, and we showed that that was also an element of the right-hand side. That's exactly what we need to do to prove this subset relationship. Okay, let's do another. So for our next result, we'll show that if the power set of A is a subset of the power set of B, then A is a subset of B. So let's really focus in on what we want to prove. So our goal is to prove this green box thing over here, that A is a subset of B. But then this power set setup is the tool in order to prove our goal. And we know that because this is part of the hypothesis, whereas that's the conclusion. Okay, so keeping in mind that we want to prove the green thing, that tells us that we should follow one of these over here. I think probably a direct proof is fine again. So let's take an element A from A. And then we want to end with that element A is in fact in B. Okay, so how do we do this? Well, we have this stuff about the power set. But what's the closest thing to a single element within the power set? Well, you guessed it, it is the singleton. So if we take A in A, let's notice that the singleton A is a subset of A. But being a subset of A means you are an element of the power set. So we might say, thus, the singleton A is an element of the power set of A. But let's recall the power set of A as a given is a subset of the power set of B. So let's strip out the middle over there and say that so the singleton A is an element of the power set of B. But if the singleton A is an element of the power set of B, that means that this singleton A is a subset of B. And we'll add that on, the singleton A is a subset of B. But if the singleton A is a subset of B, that means every element inside of that singleton is an element of B. But there's only one element, and that's little a. So we can finish this off finally. Little a is an element of B. But that finishes off what we need to do. We started with A as an element of A, we ended with B, A as an element of B, and we used the tool at this step right here. Okay, so now let's move on to showing set equality. Now we're gonna show how to prove one set is equal to another set. And this is technically a biconditional. So to show that capital A is equal to capital B, we would show little a as an element of capital A if and only if little a is an element of capital B. And so I've got this as an outline down here. So what you really need to do is show these two subset relations any way you want. So that capital A is a subset of capital B and capital B is a subset of capital A. So now let's look at this example. We want to show that the set of all integers that are congruent to 0 mod 10 is equal to the intersection of the set of all integers that are 0 mod 2 and the set of all integers that are 0 mod 5. So how are we going to do this? Well, we'll follow this outline. And just to say which direction we're doing first, I'll indicate that with a subset symbol in a box. So this means we're going to start with an element of the left-hand side and show it's an element of the right-hand side, and then we'll reverse that. So let's suppose that M is an element of the set of all integers that are congruent to 0 mod 10. Okay, great. But what does that mean? That means that M is 0 mod 10, but being 0 mod 10 means that you're a multiple of 10. So we can write M as 10 times k for some k in the integers. But now we just factor 10. So let's maybe put it as an observation or a note. We have M is equal to 2 times 5k, and M is equal to 5 times 2k. But that tells us that M is congruent to 0 mod 2, and M is congruent to 0 mod 5, respectively. Finally, that tells us that M is an element of that intersection on the right-hand side. So in other words, M is in the set of all integers that are 0 mod 2 intersect the set of all integers that are 0 mod 5. And now we've done half the proof. We've shown that this set on the left is a subset of the set on the right. And now we'll do the other half. So now we'll do the other direction, which I'll indicate with the subset symbol going the other way. So now we want to suppose that we have an element M from the right-hand side. So that means it's in the intersection of these two sets. So the set of all integers that are 0 mod 2 intersected with the set of all integers that are 0 modulo 5. But what does that mean? That tells us that M itself is 0 mod 2 and M itself is 0 mod 5. That's the entry fee to be in each of those sets. But being 0 mod 2 means that you're even, and being 0 mod 5 means that they're a multiple of 5. So that means we can write M as 2 times A and M as 5 times B for some A and B which are integers. Multiple of 2 from this, multiple of 5 from that. But now we can set those two expressions equal to each other. So we have 2 times A equals 5 times B. Notice the left-hand side is even, which means the right-hand side also has to be even. The numbers 5 is odd, that means the number B has to be even. So we'll write that here. Thus, B is even, which means we can write B as 2 times C for some integer C. Now, putting this expression for B into this expression for M, we'll see that we're essentially done. So let's observe that M is equal to 5 times B, which is the same thing as 5 times 2C, which is equal to 10C. But if M is equal to 10C, then that means it's congruent to 0 mod 10. But if M is congruent to 0 mod 10, it's in the set on the left-hand side. So that means we have M is in fact an element of the set of all integers that are congruent to 0 mod 10. And that finishes this proof off. We started with an element of the right-hand side and ended up with an element of the left-hand side. Now let's do a more abstract example. Now we've got a bit of a more abstract example. So we'll start with any non-empty sets A, B, and C, and we'll show that A cross B intersect C is equal to A cross B intersect A cross C. So in other words, this cross product has a nice distributive property over the intersection. Okay, so since this is a set equality problem, we need to show containment in both directions. Let's do this containment first. So we'll start with an element of the left-hand side and show that it's in the right-hand side. Okay, so let's do it. So let's suppose, like I said, we have an element of the left-hand side. But notice that elements of the left-hand side are ordered pairs given that we have a cross product. So that means we have x comma y is an element of A cross B intersect C. Like I said, it's best to work with ordered pairs. Okay, but now let's strip this away into what it means for an ordered pair to be in a Cartesian product. And so that means that x is an element of A and y is an element of B intersect C. Great, so like I said, that's what it means to be in a cross product. But now we'll strip away what it means for y to be in the intersection of B and C. So we have x is in A, y is in B, and y is in C. But now let's go back to the cross product world. So let's see, since x is in A and y is in B, we know that the ordered pair xy is in A cross B. And furthermore, since x is in A and y is in C, we know the ordered pair xy is in A cross C. But if xy is in A cross B and xy is in A cross C, then it's in their intersection. So we can finish that off. We have xy is an element of A cross B intersect A cross C. But that finishes the proof of this first containment. Now let's do the reverse containment. Okay, now we're going to do the reverse containment. Notice we're still working with cross products of sets, so when we start with our starting element, it makes sense to start with an ordered pair. So let's do that. Let's suppose we have an ordered pair, I'll call it xy again, which is in the intersection of A cross B and A cross C. And I think this is going to be exactly the same steps that we saw before in reverse, but that's okay. So let's see what we get immediately. We see that xy is in A cross B and xy is in A cross C. But now let's decode each of those. So that means we have x is in A and y is in B and y is in C. So that's what we get from decoding this sentence right here. So the fact that xy is in A cross B means x is in A, and it means y is in B. And then the fact that xy is in A cross C again tells us that x is in A. That's not new information though, but it tells us that y is also in C. Okay, good. But now we'll put these back together. So we might say something like, therefore, x is in A and y is in B intersect C. So that's putting this and statement back into an intersection. But then we can finish it off. This means the ordered pair xy is in A cross B intersect C. But that finishes this direction off as needed. Okay, so now we're going to look at an interesting application of set-based proofs to a very classic problem. Now we're going to look at a nice little application of set theoretic proofs for studying a certain class of numbers. And so let's look at the definition of that class of numbers. So a natural number P is called perfect if it's the sum of its proper divisors. So here are the first three perfect numbers. There's 6, which is 1 plus 2 plus 3. Those are all of the proper divisors of 6. So when I say proper, I mean all the divisors that are not equal to the number itself. Then 28 is 1 plus 2 plus 4 plus 7 plus 14. And then 496 is this big sum right here. 1 plus 2 plus 4 plus 8 plus 16 plus 62 plus 124 plus 248. And then they go on down the line. You can find big lists of them online if you'd like to. Then after that, we're going to define two sets which seem unrelated, but they will be very related. So let's take capital P to be the set of all perfect numbers. And let's set capital A be equal to all numbers of the form 2 to the power n minus 1 times 2 to the n minus 1, where n is a natural number, and then this 2 to the n minus 1 is a prime. So it doesn't run through all numbers of this form, it runs through only numbers of that form if this object is prime. But I'd like to point out that primes of this form are known as Mersenne primes. And what we'll prove is that A is a subset of B. So, in other words, all of these Mersenne primes give rise to perfect numbers. And in fact, if we only looked at even perfect numbers instead of all perfect numbers, this would be equality right here. And an even more crazy fact is that it is not known whether or not there is an odd perfect number. So maybe there is, but we just haven't found it yet. Or perhaps there are no odd perfect numbers and we just don't know the proof yet. Okay, so anyway you have it, this is what we'll prove here, this subset relationship. And we'll do it by chasing elements through, just like we've been doing the entire video. Okay, so let's suppose that we have an element A from the left-hand side, so it's of this form. So we have a natural number n such that A takes this form here. So it's 2 to the n minus 1 times 2n minus 1, where 2n minus 1 is prime. But then the fact that that's prime really allows us to write down the factors of A quite easily. So now let's list the factors of A. So the factors of A are, so they break up naturally into two classes. Not multiples of that prime number 2 to the n minus 1, or multiples of that prime number. So let's maybe break those into 1 and 2. So 1 will be not multiples of that, whereas 2 will be multiples of that. Okay, so if you're not a multiple of this part, which is prime, then you must be a power of 2, because that's all that's left over. So that gives you 2 to the 0, 2 to the 1, 2 to the 2, ending at 2 to the n minus 1. So you have all of those factors of A. But then you also have the factors of A that include that prime 2 to the n minus 1. But you have all of those factors multiplied by all of these factors, or these powers of 2. So you would have 2 to the 0 times 2 to the n minus 1, 2 to the 1 times 2 to the n minus 1, all the way up 2 to the n minus 2 times 2 to the n minus 1, and finally 2 to the n minus 1 times 2 to the n minus 1. But now let's underline all the ones that are proper divisors. So these are all proper divisors, and these are also all proper divisors. This number right here is A itself, so we won't include that in the sum. So now let's sum the divisors and see that we get A back. So let's maybe note that we're doing that here. So summing the divisors gives us 2 to the 0 plus 2 to the 1 all the way up to 2 to the n minus 1, plus, I'll maybe factor this 2 to the n minus 1 out of the whole thing. So we'll have 2 to the n minus 1, and then we'll have a 2 to the 0 added all the way up to 2 to the n minus 2. But now these are finite geometric series. So those have a well-known closed form that I bet you learned in an integral calculus class or a second semester calculus class. So let's sum those up. So this first one right here, which maybe I'll underline in yellow, turns into 2 to the n minus 1. So again, that's from the finite geometric series summing rule. But then we'll have a 2 to the n minus 1 that comes down here. And then we'll have this, which is coming from this brown underline, which is 2 to the n minus 1 minus 1. But now we can add those two together and we'll see that we get 2 to the n minus 1 times 2 to the n minus 1. But that's exactly equal to our starting number A. So we started with the number A from capital A, and then by showing that the sum of all its divisors equaled itself, that shows you that it's a perfect number, which means that A is an element of this set P. But that's exactly what we needed in order to show that subset relationship. Okay, so now I'll leave you with some warm-ups. So I've got 4 warm-up exercises to practice based on what we just saw. The first is to show the set of all integers that are 0 mod mn is a subset of the set of all integers that are 0 mod m intersected with the set of all integers that is 0 mod n. Then furthermore, sometimes this subset relationship will be inequality. And I think it's a nice extra exercise to give an example where you have equality and where you definitely don't have equality. Okay, so the next one is to prove that A is a subset of B if and only if A union B is equal to B. And then next, you'll need to show that the intersection over all natural numbers of the open interval from -1 over n to n plus 1 over n is the closed interval from 0 to 1. And then prove the union from n equal 2 to infinity of the closed interval 1 over n to n minus 1 over n is equal to the open interval from 0 to 1. And that's a good place to stop.